All right, good morning, everyone. Yesterday we looked at Newton's third law of motion. Just to recap everything from the beginning, Newton's first law of motion describes what happens or doesn't happen to an object based on whether the forces on that object are balanced or not balanced. So when you have an object that is under the influence of multiple forces, sometimes those forces balance out, like a sign hanging from a ceiling. Maybe it's got a wire supporting it that's connected to one wall and another wire that's supported at some angle to the ceiling. There are forces acting on that sign, but since the sign is not accelerating, those forces are balanced. And Newton's first law says, among other things, that in that case, the velocity will not change. And the velocity of that hanging sign is zero, and it remains zero because the forces are balanced. A very similar situation, although it seems different, but it's the same in terms of forces, is a car moving down the road at a constant velocity. There are forces acting on the car, but they all add up to zero. They are all balanced. So Newton's first law says since the forces are balanced, the acceleration will be zero. On the other hand, the other side of the coin for Newton's first law of motion is if the forces are unbalanced, in other words, there is a net force, then there will be an acceleration. So just to summarize this for Newton's first law, and this isn't the first time I've written this, Newton's first law basically says two things. If F net equals zero, the acceleration equals zero. So if F net equaling zero means the forces are balanced. Acceleration equals zero simply means the velocity of the object doesn't change. If it's sitting there at rest, then it will continue to sit there at rest. If this is true and the object happens to be moving at 3 meters per second south, then it will continue to move at 3 meters per second south. And again, the other side of the coin with Newton's first law is if the net force is not zero, and all that means is there's some imbalance to the forces acting on the object. Maybe there's more force left than right. If the net force is not zero, which means the forces are not balanced, then the acceleration will not be zero, which means that the velocity will change. And a number of things can happen. The object can speed up. That would be a change in velocity. The object can slow down. That would be a change in velocity. The object could change direction. We have a whole unit on circular motion where we talk about that. But as soon as you have an object changing direction, then there is an acceleration. What does the second law say? Well, the second law quantifies this. It gives a formula to this idea that the net force is related to the acceleration. It says that the net force acting on a single object is the product of the mass and the acceleration of the object. That's what the second law says, really. And that's kind of a summary up to but not including yesterday. The third law is more nuanced. It's a little bit more difficult to think about. Because when we talk about the first law and the second law of motion, we're talking about an object that's in isolation. I shouldn't say it that way. We're talking about only looking at one object. Okay, so we might have done problems dealing with this stuff with the second law, where you have a statement that says a baseball experiences a certain acceleration. What is the net force on the baseball? But the fact of the matter is, to get the baseball to accelerate, you have to hit it with a bat or throw it. And that brings in the second object. And Newton's third law, which is what we studied yesterday, says that when two objects interact, and like I said, it's nuanced. The only way I can get an object like this pen, very uninteresting object, but the only way I can get this pen to undergo a change in its velocity is to apply an unbalanced force. But that means something else has to make contact with the pen. So the pen doesn't just accelerate on its own, it accelerates because it's making contact with some other object that's making contact with it. Those two objects are working together against each other. So this is about two objects interacting. Whereas the first and second laws are about a single object kind of just looked at in isolation, even though there always was a bat acting on the ball, we just didn't talk about it. With the third law, what does the third law say? It says that the net force acting on object A will be, and I didn't write this down yesterday because I thought it was difficult enough to put it into words, but now I think you can handle this formula, is equal to, well, I'll write this. Let's say A is the ball and B is the bat. Is this a true statement? It is not, but it is now. So this is a nice mathematical way of saying the two forces are equal in magnitude but opposite in direction. If you take the force on one object and multiply it by -1 to change the direction, you'll get the force on the other object. And this leads to all kinds of applications, which takes us to the assignment. Does anybody have any questions you would like me to go over here from this assignment? Yeah.
On page 7.
Certainly. So what I'm actually going to do is I'm going to go back to example 5, which was the one we didn't do. And we're going to take a few minutes and just talk about example 5, because then example 7 is pretty much the same. And once you wrap your head around example 5 from yesterday's lesson or around assignment question 7, once you can wrap your head around it, they're a lot simpler and quicker than this beast. I mean, look at all the work we had to do to find, for example, the force that A applies to the hand. We had to go through all these steps. And it's because there were 3 objects in question 4 yesterday. So now let's take a look at this. You have 2 boxes. We're given both masses. There's some applied force that somebody is applying to object A. And we want to think of object A as separate than object B. It doesn't really help us to think of, not usually help us to think of that force being applied to the total mass, okay? Because we have to work backwards. So this force causes both objects to accelerate at 3.4 meters per second squared. Let's analyze the forces acting on object B, on box B. I'm just going to pull this off of here. And I'm just worried right now about drawing the forces on B. There is an undeniable fact that since B accelerates to the right at 3.4 meters per second squared, that the net force on B is to the right. Okay? And what we would have done with a similar example yesterday is we would have simply said, and I hope what I'm about to tell you triggers your memory in this regard, we would have simply said that this force on B by A, I wrote this down yesterday. It was box C, though, because there were 3 boxes. And I said to you guys, who can tell me why that force is the net force? And I think it was Ryan who said, because it's the only force. Is this force acting on B by A the net force in this question? No, because there's a force of friction. And this is just a rudimentary introduction to the idea of friction. But if there's a force of friction, that friction will always act opposite to the motion. You know, like I said, if I have a big heavy object on a concrete floor and I try to push it in one direction, I feel resistance in the other direction. If I walk around to the other side of the object and try to push it in the opposite direction, I still feel an opposing force. Friction is this weird thing that always opposes the motion. And we're going to be studying friction in detail over the coming days. But that means there's a force of friction acting on the box backwards. Why is this diagram a really, really lousy diagram at this point in time? Noah?
Well, because
Right. We know it's accelerating to the right. We're told that. And that means the net force acting on this box must be to the right. But if you look at what I've drawn, that is not an unbalanced force to the right. That's an unbalanced force to the left, which means that this is smaller than this force. And I don't really care how much smaller it is. We can't tell yet. We have to do some calculations to determine that. So it doesn't really matter. But we do know that this opposing force of friction, and I can write F friction here. We use FF for F friction, is 20.5 newtons in magnitude. And I want to go slow here, not because this is a little bit of a tricky question, but because the principle behind what we're doing here, we're going to do for the next 4 or 5 lessons. Well, except for today. Today we have to take a little detour and talk about something different. It's a tool for moving forward. The strategy that we're going to be focusing on is when you look at your free body diagram, and you should get used to the fact that that's how I abbreviate free body diagram. It's how Alberta Ed does as well. That our free body diagram is a way to develop an equation for this specific situation. And our free body diagram could be wildly different in as many as a dozen or 2 dozen ways, which means your free body diagram can lead to a dozen or 2 dozen different equations depending on the situation. And essentially, it's this. This is the tool. You use Newton's second law. I know we're dealing with a Newton's third law problem, but you deal with this statement. And again, I'm going to, are you okay with that? Okay. I'm going to do that because we've got this is important. We've already taken the directions into account in our diagram. We're not going to take them into account in the equation. So on the one hand, F net equals ma, without fail, always, always. But on the other hand, when I look at this is my eyeball. When I look at that, I can see the net force is this unknown force forward minus 20.5. So on the one hand, I can say as well, the magnitude of the net force is equal to, I don't know why I'm using green, doesn't matter, the magnitude of the force on B by A minus the 20.5 newtons. So I'm really stressing here that we don't worry about the magnitudes, and I'm taking this opportunity not just to explain this question and number 7, but to really train you and condition you to the idea that you're saying F net equals ma, and then you're looking at a diagram and saying what F net is. But listen, if F net, give me a minute, is equal to ma, and F net is equal to this unknown force minus 20.5, then this must be equal to this. So you're kind of marrying together the 2 ways to describe the net force. I can describe it by going ma, or I could describe it by adding the forces. So when I add the forces to get this unknown force on B by A, I hate this, having to write this, but I think it's important that you understand which force it is. Minus the 20.5 will equal ma. And this is not maybe exactly how we would have done it yesterday. I think yesterday we would have calculated ma and said this is the net force and gone from there. But I can put the numbers in now. This force on B by A, another way I could abbreviate it, is going to be equal to ma. Well, what is the mass of this box? 9.4 kilograms times the acceleration, 3.4? Yeah, thank you. 3.4 meters per second squared plus 20.5 newtons. And can you do me a favor, everybody? Just calculate the 9.4 times the 3.4 first. I just want to know what that is. Have you got it, Joseph?
31.96.
31.96 newtons. So this force that A is exerting on B will be, 31.96? 31.96 newtons plus 20.5. And that's going to be the answer, okay? But I want to try to get you to imagine why this makes sense, or why it could make sense. When you calculate MA, you're calculating the net force, right? So it requires, I'm going to call it 32 newtons. It requires 32 newtons of force to accelerate this mass at that rate. So why do we have to add the 20.5? If this is the force needed to accelerate the object, 32 newtons, why do we got to add the 20.5? Noah?
Because you have the object, the friction that's pushing back on it, so it kind of cancels out the first 20.5.
Right. If you applied 32 newtons, not all, force isn't like water that gets poured into an object. But if I apply 32 newtons, not all of that 32 newtons is useful in moving the object. I'm going to lose 20.5. I have to push, and we'll talk about this next week when we introduce the concept of friction. I have to push up to 20.5 newtons before the thing even starts moving. If it's a force of friction of 20.5 newtons and I push on it with 20.4 newtons, nothing happens. So, out of my force wallet, I gotta pay 20.5 newtons, and then I can worry about the net force. Anyway, this is how you would get that question. And I hope you're fine with me saying that when it comes to number 7, I would be happy on Monday to go through number 7 with anybody if they have difficulty, but I think you could work out number 7 now. And maybe I better be careful because I don't know that we've actually finished the question. Calculate the force exerted by box B on box A. Okay, we have not finished the question. This force that we've found is to the right, and it's the force that A exerts on B. So what is that? 32. This works out to, can I just say 52.5? Is that what it rounds to, newtons? But that is a force, looking at the diagram to the right. It is not everybody to the right because I have a positive number here. It isn't. Because we're going to have cases where the objects will accelerate to the left, but we'll still get a positive. Because when we set this part up, it's bigger force minus smaller regardless of the direction. Okay. So in answer to the question, they're asking here in this example to find the force on A by B, and this is the force on B by A. So the answer to this question is 52.5 newtons rounded left. And really, you know what? To go from here to here, that's the only part of this that is Newton's third law. Everything else was an application of Newton's second law. Does that make sense?